I would now like to conclude by applying the Anova test to this example of 6 different smoking groups, and we're going to compare the mean forced expiratory flow for each of these 6 groups. So I'm going to start by recording some of the information that we need. So the number of groups here is 6. The total number of observations is 1,050. There were 200 in 5 of the groups and 50 in one of the groups. Okay, and then Y double bar is going to be the overall mean. And so what that's going to be is a weighted average of the sample means. Okay, so the first sample mean was 3.78 for that first group, and there are 200 samples in that group. I'm going to multiply those together. The second group mean was 3.3, and again, I'm going to multiply by the number of samples, which was 200. The third group, I think it was the non-inhaling group, is 3.32 for the sample mean, and that only had 50 observations. Okay, the next group had a sample mean of 3.23, and that had 200 individuals in it. Okay, the next group had a mean of 2.73, and it had 200 individuals in it. And then the last group had a sample mean, I think that was the heavy smoking group, of 2.59 with 200 individuals in it. Okay, so if you compute that weighted average, you're going to get 3.135. And I have to say, this is one of the areas in which students tend to make mistakes, in that they try to just take the 6 sample means and then just add them up and divide by 6. But you have to take into account the sample sizes. We have to weight this average by the sample sizes. So you take each sample mean and you multiply it by the number of individuals in the group. Okay, and then add that all up. And I think the last thing that I didn't do here is I didn't divide by 1050 the total number of observations. Otherwise, it would not make sense that I would have gotten an average of 3.135. Okay, so that's how we're going to find the weighted average. Okay, and now I want to calculate the sum of squares between and the sum of squares within. And I'm going to use this table here to kind of help me organize everything I need for the test. So I'm going to go ahead and calculate the sum of squares between. So the sum of squares between, I'll remind you, is a weighted average, or it's not quite a weighted average because I'm not dividing by anything yet, but it's a weighted sum of the sample sizes times the difference between the group mean and the overall mean squared. So what's that going to look like? Well, I'm going to have 200, and then that first group mean we saw was 3.78. Okay, so maybe I'll put that back here so that we can see it. And then I'm going to subtract the 3.135, and I'm going to square it. And then I'm going to have 200 times 3.3 compared with 3.135 squared, and then 50. I'm going to take the 3.32 and subtract 3.135 squared. Then I've got 200 individuals where I take the mean of 3.23 and subtract 3.135 squared. I think those were the light smokers. And for the moderate smokers, there were 200. I'm going to take the mean of 2.73 minus 3.135 squared. And then for the heavy smokers, I've got 200 times 2.59 minus 3.135 squared. Okay, so the sum of squares between, when I add that all up, is going to be 184.376. So I'm going to record that here in my table, 184.376. Now my degrees of freedom between is the number of groups minus 1, so that's 6 minus 1 is 5. Okay, and so if I do the division for the mean square, so 184.376 divided by 5 is 36.875. And I now have the mean square between, which is the numerator in my F statistic. So the mean square between here is going to be 36.875. Now I need to do the sum of squares within, and here I'm going to need the variances. So my sum of squares within, well, that's going to be the sum over all the groups. And I'm going to sum n minus 1 times the variances. Okay, so what's that going to look like? Well, n minus 1 for the first group is 199, and the variance is 0.78. The second group is going to also be 199 for n minus 1, and then the variances were 0.77 squared. And then 49 for the third group, that's 50 minus 1 times 0.86 squared. Okay. The next group will be 199 times a variance of 0.78 squared, if we're looking back at the table. And then 199 times a variance of 0.81 squared. And then finally 199 times a variance of 0.82 squared. Okay, so I'm going to add that all up and I'm going to get 663.866. Okay, so for the sum of squares within, I get 663.866. My degrees of freedom is going to be 1,044. That's the total number of observations minus the 6 groups. My mean square is going to be 0.636 when I take 663 and I divide it by 1,044. So on the denominator of my F statistic, I'm going to have the mean square within, which is 0.636, and that's going to give me a total of 57.99. That's going to be my F statistic. Now that already seems quite large, even though I don't exactly know what that'll look like on the chart, but it does seem kind of large. So what I'm going to do is I'm going to refer to the chart to find the p-value. So I'm going to go to an F distribution chart. Now, I'm going to go back up to the top of this chart. It says critical values of the F distribution, and the first chart says numerator degrees of freedom equals 1. So this is for 2 groups. Okay, so if we were using Anova on 2 groups, then the degrees of freedom would be 2 minus 1 or 1. Okay, so we're going to go down to degrees of freedom not 2, that would be for 3 groups. Okay, but we're going to just keep scrolling down until we get to the degrees of freedom in the numerator of 5. So this is a series of charts. Okay, so this is actually for 6 groups. Okay, and then what we're going to do is we're going to go down to the denominator degrees of freedom of, oh, it's not even on the chart. So 140 is the highest number that we have. Remember, we had a denominator degrees of freedom of 1,044. Okay, so what would have my cutoff have been? My cutoff for 5% would have been just 2.28. Okay, so my F, okay, for 0.05 being my 5% cutoff that I'm willing to live with. The degrees of freedoms would have been 5 and 1044. That cutoff was 2.28. Okay, but it turns out that is our test statistic, right, which was 57.99, is much higher than that. In fact, it would be off the chart over here. 57.99 would be off the chart over here. So our p-value would be less than even 0.0001. Okay, so this is going to be very highly significant. Okay, so here we're going to get a p-value that's less than 0.0001. Okay, so there is sufficient evidence to suggest at least one population mean of forced expiratory flow is different from the others. But you might think that that is not a real satisfactory conclusion. I can say, well, at least one of the groups is different from the others, but which one is different from the others? Is heavy smoking impacting mean FEF? Moderate smoking, light smoking, passive smoking? What non-inhaling? What is affecting the mean forced expiratory flow here? Okay, I don't know which groups are different from the others. Okay, and so I encourage you to watch the next video on what are called post hoc tests, because that is the way in which we can resolve this unsatisfactory conclusion in which I know one of the population means is different from the others, but I don't necessarily know which ones. I'm going to finish with some important important things about applicability of Anova. I want to know when the Anova test is going to be valid and when I can use it. Okay, the groups must be independent of each other. Okay, so we can't have the same individuals across groups. Okay, we can't have like maybe members from the same families across groups or things like that. The groups must be independent. Observations in each group must be random samples. Okay, so I have to be able to basically do kind of t-tests with each group. Okay, so I need observations in each group to be random samples. The sample means must be normally distributed. Okay, normally distributed, meaning that each group must have a normal distribution for the data, or each group must have 30 samples. So this would be n put I greater than or equal to 30 for each group to make sure that the sample means are normally distributed. And then this is a new one, but the group standard deviations must be approximately equal. Okay, and what do we mean by approximately equal? Okay, we don't want, if we have one standard deviation is, say, more than twice another standard deviation, then this violates our assumption. Okay, so if you have one standard deviation that's more than twice the other standard deviations, then that would violate our assumption. And if you like, we can kind of go back and look at our summary data for our table, and you'll notice that all of our standard deviations are between, say, 0.77 and 0.86. Okay, so they're all roughly the same. So we were able to satisfy that assumption that the group standard deviations are approximately equal. So I encourage you all to watch the next video in which we look at a post hoc test that will help us determine which of the smoking groups are different from the others.